Okay, geometry fans, our topic for today is symmetry, notes section 3-5. After this lesson, our goals are to explain the three types of symmetry, line, rotational, and point, and to determine whether a figure is symmetric to a line or a point. Before we start, let me give you your joke of the day. What do a dog and a phone have in common? And the answer is they both have caller ID. Collar, C-O-L-L-A-R, for a dog. Okay, the idea of symmetry, this is a topic that you have looked at before. You've seen it probably in science class. You may have seen it in a previous math class. The idea of symmetry is to map or fold an object onto itself. So map or fold, I'll say a figure, onto itself. I can think back to when I was in elementary school and it was Valentine's Day and we had to draw hearts in art class or we had to cut them out. And even as an elementary student, you can see that the heart will have symmetry if you've drawn it that way. So you can draw a line that goes through the heart where the left side basically equals the right side, or it folds or maps onto itself. One side maps onto the other side. Now, vocabulary, we don't have a lot of vocabulary here, but one thing is the concept of being a regular polygon. A polygon is just a shape. It's a closed figure. A polygon is a closed figure in a plane. So a triangle, a quadrilateral, a pentagon, a hexagon. But what it means to be regular is that all the sides and all the angles are congruent. To be a regular polygon, all the sides and all the angles are congruent. Now I'm going to come back to that in a minute. Okay, we'll talk about what that means. Line symmetry, there are three kinds of symmetry that we talk about. First one is called line symmetry, and the idea there is you can fold a figure across a line. Fold a figure across a line. So for example, for the heart, I can fold the left side and it fits perfectly onto the right side. Or I could fold the right side and it fits onto the left side. So let's look at some shapes here. A regular quadrilateral, well, we have a name for that, where the sides and the angles are all congruent. If it's a four-sided figure, then that is what we call a square. So let's go ahead and draw a square. Well, try to draw it accurately. Now, assuming that we've drawn this perfectly and we know that again, the four sides are congruent, there are different ways that we can draw a line that would make part of the square symmetric to itself. We could draw a vertical line, okay, that goes through the midpoints of the top and bottom where the left side folds onto the right. We could also draw a line of symmetry horizontally where the top folds onto the bottom. Now, if it's a square, we could also draw it diagonally, where this triangle will fold perfectly onto this triangle. Or we could draw it the other diagonal. That's a terrible line right there. But with a square, there are four lines of symmetry. So if you have a square, you have four lines of symmetry. Depending on the figure, you may only have one line of symmetry. You may have no lines of symmetry. In a square, we have four. Now let's say that we take a rectangle. Now we could draw a vertical line of symmetry. We could cut it in half like that. The left side folds onto the right side. We could also cut it in half horizontally, where the top folds onto the bottom. Now this one you have to be careful. It does not work diagonally. This point here would not fold onto this point. If you take a piece of paper, like a regular sheet of paper, you would see that it does not, in a rectangle, those points will not match up. So you can't have, the diagonal one doesn't work. So in a rectangle, we only have 2 lines of symmetry. Okay, this one is no good. Okay, I'm gonna kind of scratch that out. Now, if we draw triangles, it depends on the kind of triangle. A regular triangle means that all the sides and angles are congruent. Well, that's what we call equilateral. Okay, so we know that. Now, if it is equilateral, we could draw a line of symmetry vertically, where the left and the right side would fold onto each other. But because it's equilateral, and by the way, this line would be an angle bisector here. These would be 30 degrees. Because in a equilateral, it's 60, 60, 60. We could also draw one this way, and we could draw this way. So there would be 3 ways, 3 lines of symmetry here. So when we're doing this, in terms of a triangle, the lines of symmetry would be segment bisectors, and they would also be angle bisectors for that. Now, if the triangle is isosceles, let's draw something like that. You could still draw a line of symmetry vertically, up and down. Again, that's not very good. 1 line of symmetry. The problem is that it wouldn't work if we try to draw it from another vertex, from these 2 vertices. If I try to draw that, again, this will not fold onto this. It's not going to fold perfectly. So for an isosceles triangle, there's only 1 line. If you had a scalene triangle, so isosceles, 2 sides are congruent. If you had scalene, there would be no lines of symmetry. There would be no way that we could divide that up, that we could fold 1/2 perfectly onto the other. Okay, so line symmetry is just looking at a figure and using a line basically to divide the figure in half so that one side folds onto the other. Now, a second kind of symmetry is called rotational symmetry. If a line symmetry is where you fold a figure across a line, rotational symmetry is where you rotate or turn a figure onto itself. Where you turn a figure onto itself. All right, so what does that mean? Well, as an example, let's say that we take a triangle, and let's say it's an equilateral triangle. If you take the 3 vertices, and you can almost think if I put a circle around this, how many degrees would we need to rotate this so that this point would rotate to here, and then this point would rotate to here, and this would rotate to here, where we could rotate the figure and it would still look the same. It would be pointing in the same direction, the orientation would be the same. And in a equilateral triangle, if you think of the circle here where all of these turns would be equal, they'd each be 120 degrees. This triangle has rotational symmetry, and the rotational symmetry would be 120. If we took a square, again, how many degrees to get from one vertex so that it would rotate onto the next one all the way around? Well, that would be 90 degrees. Rotational symmetry. So these have line symmetry, yes, but they also have rotational symmetry. How about a rectangle? Now, a rectangle is going to be different. To rotate this, if I only do 90 degrees, if I rotate this 90 degrees clockwise, it's going to look like this, which is not the same orientation as this. So 90 degree would not work. However, if we did 180, if we did 180, where basically this side, if you turn it 180 degrees, this would rotate onto here, and then this segment would rotate to here. So we'd basically turn it like that. So a rectangle would have 180 degree rotational symmetry. Now one more example that I'll draw here. Let's say we go back to the isosceles triangle. That has no rotational symmetry. If I rotate that 180, this would be upside down. If I spin it 180 degrees. If I try to spin it 60, it would be pointing off somewhere this way, like this. So this triangle has no rotational symmetry. Okay, so again, some figures do, some figures don't. If you have a circle itself, a circle would have 360 degree rotational symmetry. No matter how you turn it, you're going to see the same picture over and over. The third type of symmetry is called point symmetry. Point is actually a very special kind of rotational symmetry. It would be 180 degree rotational. So it's a special case, basically. It's a specific example of rotational. So for example, I'll go with the rectangle again. If I put the point here, if I spin it 180 degrees, this point would rotate to here. This point would rotate to here. Okay, and then these 2 points would rotate onto each other. So that would be rotational symmetry. Another example, I'm going to draw a figure here that's this is going to be a confusing figure, but if I take, here's the point, so it's going to spin around the point. If I draw something like that, and then like that. Okay, now again, you have to kind of imagine if I turn this halfway, this would rotate to here and this would rotate to here. It doesn't matter if I go clockwise or counterclockwise. Okay, so this though would have rotational symmetry. Now something that would not, let's take that equilateral triangle. This would have 180 degree rotational, so that would be point symmetry. This has rotational symmetry. We already said it's 120 degrees, but if I go 180, the problem is that it's going to look something like that. And that's not the same orientation. So that would be no. Equilateral triangles would be no. Any triangles would be no. If we draw a pentagon, that would be no, because this part, if we rotate 180, would be pointing down. Now, if we take a hexagon, assuming that this is drawn perfectly, this would be rotational. It would be point symmetry, because if I rotate that 180 degrees, it would go to there. So that would be a yes, pentagon would be a no. And that is the end of part 1.